Schmoldt is the national program leader at NIFA. Okay? He has a lot of experience in agricultural robotics. He has about $100 million plus portfolio of grant programs for specialty crops, robotics, engineering, nanotechnology. Okay? He also the joint editor-in-chief for the Journal of Computer and Electronics in Agriculture. Okay? And since 2001, he started to become the national program leader for Instrumentation and Sensors for National Institute of Food and Agriculture. Right now, I guess you are also one of the NI program manager for robotics in agriculture. That's all.
Thank you, Herman, and thank you for inviting me here to be part of a panel of fairly distinguished speakers this afternoon. I say fairly because my only distinction probably is I'm the only one that hasn't been affiliated directly with NREC or the Robotics Institute at Carnegie Mellon. So I'm a bit of an outsider. Maybe that's a good thing. It sounds like agricultural robotics has been a great interest here for quite some time, thanks to Red and others. And we have had an opportunity at NIFA to fund some of that work. How many, I see quite a few young faces, how many of you were here when President Obama was here in 2011? No, Red was here. Maybe a third. I'm a little bit, what should I say, I'm not a big fan of those sort of press events, those high-level press events, but the National Robotics Initiative that was kicked off that day, I think has had a big impact on not just ag robotics, but robotics in general in this country, and has made a difference in terms of elevating the national capability in robotics. And I know from an ag perspective, it has given us lots of opportunities to fund some new and interesting projects. So I want to cover some of those today. And I've been asked by Herman also to talk about what I'm projecting or futuring or trending going forward. Some of you probably were here for a talk I gave last December, so you'll see a few similar slides, but hopefully I have enough different slides, and the second half of my talk will be something new and different for you. Before I do that, I have a couple slides, and I always insist on doing this just to give people an understanding of what USDA means. The National Institute of Food and Agriculture is just one agency in a very large department. The department, USDA is the second largest civilian employee outside of the Department of Defense. And we have, you can't read this, you don't have to, we have 7 mission areas with agencies in these various mission areas. This is the mission area that does most of the R&D. We have 2 agencies here that do intramural research, the Agricultural Research Service and the Economic Research Service, and then NIFA is the primary extramural funding agency in USDA. To give you a sense how important R&D is in the USDA outlays, this is for 2016, and you can see almost 3/4 of the USDA outlays are for expenditures are for nutrition assistance. Used to be food stamps, now it's called Supplemental Nutrition Assistance Program. And that's mandatory funding, everything else is discretionary. And it includes conservation and forestry, the National Forest System, for example, commodity programs, and then the other 6% includes inspection and rural development and R&D. So R&D itself is probably between 2.5% and 4% of the overall USDA budget, so it's not big. And then one slide about U.S. agriculture. Red knows probably some of this. Some of you may know some of this, but you may not know a lot about where we've come from. If you look at the historical trend through the 20th century and the number of farms and the size of farms, they flip-flop. And so We have about 2.2 million farms now, and there's a fairly low bar for what USDA defines as a farm, and it's any operation that generates $1,000 in revenue. The average age of U.S. farmers is 58. I don't know if you can imagine farming at 58. In Japan, it's much higher, closer to 68. When a lot of us have retired or thinking about it. Over half of the farms are 100 acres or less, so lots of small farms. And many of these farms are operated by people that have an occupation off the farm or are retired or partially retired. But in terms of farm gate value, 90% of the farm gate value is generated by 10% of the operations. So it's a 90-10 rule. U.S. is a net exporter of agricultural products, and just farm gate value accounts for about 1% of GDP. If you include the whole food and fiber system through to retail, it's about 12% of GDP. I'm sure many of you have heard a lot of these projections. You see them all the time in the news. We're looking at potentially more than 9 billion people by 2050. So we need to double food production in the next 35 years. That's assuming we're in 2015. And part of the reason we have to double food production is we currently have people that are food insecure, and so we need to get more food for those folks. Plus, as people move into middle income brackets globally, their diet changes and they want more protein, which puts more pressure on our food system. We have a lot of irrigated land in the U.S., so that's and both surface water and subsurface water is becoming depleted, and with climate change looming, that's the big wild card. We're going to have extreme weather events. Welcome, Louisiana. New pest pressures and regional changes in productivity, all of which are going to create increased risk in our food and fiber systems and make shortages more likely. And the number of people globally that are expected to become food insecure is going to grow. So not a lot of good news there. In terms of agriculture, because it's an important activity in terms of food, fiber, and biofuels, as well as feed for animals. 50% of U.S. land is devoted to agricultural production, and by agriculture, we're not just talking about food, but forestry is also part of agriculture, and that's where a lot of the fiber production comes from. 10% of the energy budget is consumed by agriculture, and 70 to 80% of the fresh water in the U.S. Somebody decided it was a good idea to grow cotton in the Arizona desert, for example. 20 million tons of fertilizer are used annually, as well as many other tons of herbicides, fungicides, and pesticides. Globally, we're approaching the limit of arable land, and still, at least in the U.S., the food waste issue is not as bad elsewhere, but in the U.S., we waste 40 to 50% of the food that's produced, and it's lost throughout the food system. First at the farm, then through harvest, processing, distribution, and yes, consumers. How many of you have thrown out broccoli that got yellow? A lot of food is wasted. It doesn't need to be. So the overall goal then is to be, well, first of all, have sustainable ag systems, which means meet productivity needs in terms of the food and fiber and fuels, while maintaining environmental quality, have economic viability for those that are involved in agricultural production, and provide a quality of life, good jobs, as well as reasonably priced, not cheap, but reasonably priced and available food for everyone, food and fiber for everyone. So one approach then is to develop engineered devices, products, and systems that can precisely reason, sense, reason, and respond. And the intent is to improve productivity, profitability, and efficiency in the ag-related operations of all sizes. As you saw, a lot of our growers, producers are small operators, and those need to be part of the equation as well, even if they only represent 10% of the total production value, and benefit consumers and society in terms of jobs and the outcomes for the products from agricultural production. So the first bullet, I mentioned most of that already. The second thing, especially when you get into cropping systems and crops that require a lot of labor, is it's oftentimes unavailable, and it's also very expensive when it is available. And this creates an economic disadvantage if you're competing in the global marketplace. The expectation is that robotics will be able to, do I have a pointer here? Maybe I do. Which is the pointer? This it? Yep. I got it. Thank you. If robotics can help us be more productive and efficient, it reduces our environmental and ecological footprints in consuming resources and generating waste. And then this is the job aspect down here, the workforce. Getting rid of these dirty, dull, and dangerous jobs. And growing up on a farm, it's mostly dirty. It's also very dangerous, but it was mostly the dirt that bothered me. And replace those with higher wage, technically demanding jobs. And I'm going to talk a little bit more about workforce towards the latter part of the talk. And when you combine these together, that's what we mean by agricultural sustainability. So I wanted to talk a little bit about the National Robotics Initiative and some of the projects that we funded. Over the first 4 years, this is the amount of money that we obligated, a little over 15 million total, and 19 projects. Actually, we've committed a little bit more money because some of the projects we funded in 2016 are continuation projects, which we didn't give them all the money this year, but we sort of promised if we had the money and they perform well, that we'll give them the remaining money in 2018. So, and the average award amount was just under $900,000, and these are 3-year projects. I'm going to skip through a couple of these in the interest of time, because I want to get to the latter part of the talk. This is a project we funded, I think, our second year out of the University of California, Davis, Stavros Fujiokas. Rather than solving humans are really good at some things. They have the dexterity to harvest, in this case, strawberries. And rather than try to duplicate what people are doing, to make the process more efficient by adding robotics to aid the pickers, and so that they can do what they do well. And the idea was to provide a little courier service to actually carry these boxes of strawberries from the pickers down these long rows, because otherwise they have to carry them down the rows, and it's very dangerous walking down some of these narrow rows, and their picking efficiency drops dramatically. So they borrowed some ideas from flexible manufacturing and minimizing pickup delays and non-picking times, while still providing proper ergonomics in terms of stopping or stooping time, and they can't be picking all the time. They need to have breaks, and there are legal requirements for that, and those sorts of things. So they developed this interesting little cart, and have a brief video here. There'll be some sound, but you don't really have to hear it to get the idea. It is a nice little song, though. And so they have to coordinate between themselves and the pickers, how fast the pickers can pick, and not all these carts getting down to the end of to the loading station, all at the same time, and those sorts of things. So it was a very interesting project. I think it's still ongoing. It's nearly complete. One of the projects that was funded here at Carnegie Mellon, and this is Steve Nuske of the Robotics Institute. Some of you may know Steve. And we're talking specialty crops here. High-value specialty crops, both berries and grapes and apples. Growers really need to know what the potential yield is throughout the growing season because they make decisions about how to manage the crop. For example, green harvesting or to remove some of the lower quality fruit or just reduce the fruit load so the remaining fruit is of higher quality. And also to schedule how many pickers they're going to need and their contracts for the packing houses and those sorts of things. So they incorporated computer vision as well as active sampling and human counting to come up with better estimates. Many of the current estimates manually can be off by like 50%, and they're approaching like 95% here. So I've got a little video for this. Where's my cursor? Here we go. So it's just stereo vision cameras and flashes to create an optimal lighting condition in all lighting scenarios. So it's estimating berry size as well as ripeness and doing a count. I'm not going to play this whole video. Of course, this is all post-processed. It's typically the case. Okay, I'm going to stop that one there. In the interest of time, I'll forget this one. This is a nice one, but I'm not going to go through this one either. There we go. This is a project, and actually we're going to fund a second version of this project. Water quality is obviously a big issue in our rivers and lakes, and agriculture is not like industry where you've got a pipe coming off the farm and you can measure the waste coming off that and know if a farm is degrading water quality. There's a lot of seepage subsurface as well as runoff. Most of it's nutrients, nitrogen and phosphorus. And the only sensing they have right now for water is our stationary stations, well downstream where all the water aggregates and you don't know where it came from and where the pollution is really coming from. So they developed a UAV-based water sampler which is, can move around and collect mobile samples and be combined with static sampling and it opens up whole new opportunities for water sampling to maintain water quality. And what's interesting, I think, about this is I'll play the video here, is if you have dense enough in both spatially and temporally and water sampling throughout a watershed, then maybe agricultural runoff and nutrient pollution is no longer non-point source pollution, but it becomes point source pollution because you have this contour map of where the nutrients are appearing in the water, in the surface water. And so that may change the regulatory framework going forward. So this is an instance where robotics can really change how we do things and policies. And you can see the little samplers filling up. They have 3. I think at this point, sort of when this was taken, like the second year of the project, they had the ability to send the UAV off, give it like 3 coordinates, GPS coordinates within like 1.5 kilometers. It could go off autonomously, although they technically can't do that according to the FAA rules at that point, and collect these water samples. One other area, and I don't have any projects to show you here, although we funded 2 projects just starting this year in 2016 on high throughput phenotyping. And Carnegie Mellon's very involved in that, both here at NREC and at the Robotics Institute. And some of you may be quite familiar with what's being done. The idea is that, of course, that creating new plant varieties with particular characteristics, whether it's yield or seed count or resistance to insects and diseases, you have to get thousands of crosses based on some genetic manipulation that you've done, and then plant them out and measure them in an actual environment, because it's genetics cross environment to understand what the phenotype really is. And going back, centuries, this has always been done manually, going out there and taking measurements of these plants growing out, and trying to relate those to the genetics, and then doing further crosses and that sort of thing. And it's very error prone, it's very time consuming, and students don't like to do it, and it's all those things you hear all the time. So developing both aerial and ground robots to collect many terabytes of data on a regular basis, and relating that to the soil conditions plus the weather that season, and then doing the machine learning to identify which really are the best varieties for what you're interested in, and then eventually breeding those and producing new varieties. Just a brief survey of funded projects, and this is just like a napkin sort of analysis. The first 5 years, I sort of categorized them. Aerial vehicles, ground vehicles, and of course some projects do both. Sensing or actuation, and by sensing, of course, I don't mean situational awareness, navigation sensing. I'm talking about application sensing. And then whether it's ag production related or natural resources. And actually we had one project which I didn't show you that covers both natural resources and ag production, so it's kind of interesting. The only real surprise here, of course there's fewer UAV, well it's on the next slide, is there's more actuation than I thought. I thought it would be mostly sensing, but there's a lot more actuation going on, and that's an area that where we really need work. So some of the trends that came out of the first 5 years, UAVs, there's obviously, you've read all the press, there's huge interest by the ag community. Farmers are buying these things left and right, playing around with them. A lot of interest. But due to FAA restrictions and power challenges, there weren't that many projects this first go around in the NRI. I think that's going to change going forward. I think there's been a significant halo effect from the NRI and some of our other grant programs in the agency. We're seeing more robotics submissions, even in programs that you normally wouldn't expect it. You'd have a larger project that would have a robotics piece to it. And the number of non-traditional investigators to agriculture. I sort of categorized the projects looking at the lead institution, land-grant university. That's the group of universities we typically deal with because they have ag colleges. So how many of the projects were submitted by ag colleges and land-grant universities, non-ag colleges and land-grant universities, and then non-land-grant universities. And you can see the numbers there. Probably not so surprising because this is where a lot of the robotics is done, and less in ag colleges, and that would be the ag and biological engineering departments. And again, it's not surprising, but it was good to see that even though there were a lot of the ag colleges were co-PIs and participants in a lot of these other projects, because it's important to have that relevance, whether you're dealing with pest detection or phenotyping. You know, you need people that on your project, not just roboticists, but other people that understand the application area. Going back, 25 years, I guess now, when GIS, GPS, and remote sensing first became readily available, there was a big push in what was called precision agriculture. Well, it still is, but it was focused on site-specific management. You know, so much of agriculture is just you apply the same management to an entire field, and you don't do things differently based on crop condition or soil type or any of these other things. And having this other information, whether it's yield monitors, there were yield monitors then on harvesting equipment like combines. So you had a lot more information. You could come up with management zones. And this was largely applied to row crops. And those are your commodity crops, corn, wheat, soybeans, those sorts of things. One of the big problems was, though, that the variable rate technology, that is sprayers and other equipment, couldn't really deal well with that information, and it was hard to make management decisions based on the information you got. It wasn't actionable information. That's a catchphrase right now. So as we move into this period of time, and whether it might be Precision Ag 3.0, I'm not sure. We're talking more about just-in-time and just-in-place agriculture that relies on highly dense sensing information and actuation spaces across throughout the entire food, feed, fiber, and biofuel systems, from production to processing, handling, storage, transportation, and consumption. We're talking about technologies like active and passive sensors, cyber-physical systems. We've heard those mentioned a couple times today. Obviously, robotics, that's why we're here. And big data is a really big part of this. And because so many of these systems now are collecting so much important data, and if we can make more sense out of it, there can be both scientific as well as management innovations that can come forward from this. Key R&D areas, sensors, and again, these are application sensors, not situational awareness, navigation sensors. Actuation, we need to be able to do things, whether it's harvesting a fruit or pruning a vine, whatever it might be. Autonomy, you know, farmers, producers do not have IT departments, and they don't even have engineers most of the time, so they're not going to want to do this. They're going to want to be able to turn robots loose out there. They're happy to do that, I think, once they understand the capabilities. And of course, again, the big data, we need to incorporate from all this stuff actionable information and make sense out of it. Some of the technology challenges that we're dealing with is farmers are crisis-driven. What's the pest this week or this month or this year? What new regulations am I going to have to adhere to? We need technologies that are relatively scale neutral, that can be available to both small producers as well as large producers. And that I'm going to talk a little bit more about that in another slide. And we need robust technologies that can be applied across a variety of crops and operations. So some of the trends, and this is where I was going with the previous slide. I think going forward, and we sort of see that already, especially in some of the areas. Obviously, John Deere makes combines. They're not going to cut them into little pieces and create lots of little combines because there are efficiencies there. But for many of agricultural operations, we're going to have lots of small robots. Again, it's cost, economics. You can sell to more producers, scalability, and big equipment. You have real soil compaction problems. Here's an idea that Herman and I have been talking about a little bit. If you've got things that, like UAVs and maybe legged robots, where you're not using wheeled vehicles, do you really need rows? And if you're in a vegetable cropping system, you can probably double your acreage because you don't have, you can plant the space between the rows and you've got nothing but plants out there. Workforce skills in agriculture. Currently, colleges of agriculture graduates, a lot of those jobs that are out there in agriculture go unfilled because there's not enough people. There haven't been enough people to fill them. So there's a real demand for people with agricultural degrees, whether it's entomology or plant pathology or physiology or whatever it might be, or horticulture. Young people find robotics cool, obviously, right? I think going forward, because the incoming students are going to ask for it, I think the industry is going to start asking for it, is there's going to be the development of ag technology degrees that are going to combine robotics and other technologies with an agricultural degree of some sort. Workforce size in agriculture, and as you know, in the 20th century, there was a big exodus from rural areas to urban areas because of industrialization, and you could get better paying jobs. You can only had to work 5 or 6 days a week. So we lost a lot of people in rural areas and ag jobs. There's been a big interest in food from many people. Things like fresh and local, organic, sustainability, vertical farming, urban agriculture. The whole foodie network has created some of this is fad, but not a lot of it isn't. I think there's going to be an increased interest in agricultural jobs. Some of those may cause sort of a transition back out of urban areas, maybe not to rural areas, but maybe to peri-urban or ex-urban areas, something in between. But I think many of the agricultural jobs could actually be in urban environments with vertical farms. Row crops, again, corn, soybeans, wheat, those sorts of things. Cotton is included there. If you add animal agriculture, it's about 60% of total farm gate value. But just talking about row crops, large acreages, lots of mechanization and large equipment, plant, spray, irrigate, harvest are the primary things. I'm saying this is sort of covered by the private sector. Deere is very much into this, as well as Case New Holland. That's not to say, and there's lots of new companies working in this space as well, with UAVs and big data and those sorts of things. Monsanto's involved as well. There's still opportunities for innovation, R&D innovation, but a lot of the work is already being done in the private sector. So, there's other places to put our money, is sort of what I'm saying here. Specialty crops, which include many perennials, not just vegetables, of course. It's about 40% of farm gate value, hundreds of different crops, small acreages, many producers, very little mechanization, and a whole bunch of different operations: pruning, weeding, thinning, spraying, irrigating, green harvesting, et cetera, et cetera. And there's the labor issue. So this is an area where robotics and some of these other technologies are very much needed. Natural resource management, soil, water, air, and non-production ag. And some of the non-production issues are wildlife conservation, ecosystems and ecosystem services, for example, biodiversity, pollinator habitat, those sorts of things, dealing with climate change. Widely dispersed resources, we need to measure, count, model, monitor. This is an area where robotics can be very important. Animal agriculture. Well, we have large and small animals, except for robotic milking. There's very little mechanization. we need to monitor, sort, vaccinate, and other sorts of things. And so I think there's a real need there too, and an opportunity for robotics. Robotics is kind of interesting in agriculture because it brings a new general purpose machine, not unlike a tractor really, and to which implements or payloads of different sensor suites or manipulators with end effectors can be added. The difference, of course, with robotics brings you intelligence as well and data collection, which can lead to actionable information. I think the current hot topic last year in 2015, the NRI, we got no high throughput phenotyping projects submitted. This year we had 4. I think this is a really hot topic right now just because it's so important. And as I said, the robotic CMU is involved in a couple of these projects funded by ARPA-E. Crop-focused ag robotics, I think, will continue to dominate versus animal agriculture. The one exception might be animal monitoring and welfare. The economic incentives, of course, aren't there for natural resource management, even though they're very important. And as regulations change, they may become more important. The specialty crop arena, which is fruits and vegetables and tree nuts and horticultural and nursery crops. I think that's where a lot of the research needs to occur, and that a lot of the projects that we get submitted to the NRI that are related to agriculture are in the specialty crop arena. These are high value crops as well, so the economics is there as well. And as I mentioned, the private sector is doing a lot of commercialization and robotics in row crops. So this is not, if you didn't know before, this is not what we're talking about in ag robotics. But I put this in here because I wanted to point out, I think if we want to allay people's fears about robots ever taking over, we just need to put bow ties on as many of them as possible. They're just not as threatening now. Even if they're wielding chainsaws and armor-piercing lasers. And that's all I have. Thank you.
Any questions for them?
So when you said that the average age is 58 years old, that was like pretty shocking. Does that not include the illegal workers who are working in the fields as well?
Those are agricultural owner-operators.
Okay.
So it's not workers.
Okay.
Yeah, good question.
Also, the apple that I eat, how much of the cost of the apple that I eat is from manual labor that could be replaced by robotics? In other words, let's say the manual labor was free. How much cheaper would that apple be? Or in general, like, what do you think the market opportunity is?
Well, I think it was on one of my slides, 40 to 60% of production costs are labor. That's not just harvesting, but it's all the other operations. And those are in specialty crops like apples and, there's some automation depending on what sort of product, like there's hand harvested oranges, for example. Those are the fresh market, and then the juice ones are harvested with these big machines that shake the crap out of trees, and they drop on a conveyor and are picked up. So there's some mechanization, and then there's blueberry harvesters, there's grape harvesters. So there's some mechanization, but it's not available for everybody, or it's not right for your particular whatever you're marketing. If you're marketing really high value wine, most people hand harvest.
You noted that one of the needs of actuation specifically was on one of your slides, plug-and-play functionality. Can you give a little bit more color to the need?
Well, the idea is if The robot that's actually where you're plugging this actuator, this manipulator and end effector would have the appropriate programming. With the manipulator end effector would come the program that could then be run on that robot that would know how to move throughout whatever operation, whether it's spraying or pruning, that could move through the orchard, for example, and know how to move around and to deal with that particular manipulator. So it's like plugging in, you can plug in a USB thing in your computer, and a lot of computers will have a driver for it already. I guess that's the driver idea I was trying to convey.